Thank you for attending my presentation. My name is Justine Allpress, and I'm a research geospatial scientist at RTI International in Research Triangle Park, North Carolina. My presentation today is Advances in Big Data and the Impact on Grid-Based Sampling. The presentation will focus on three areas: the origins of grid-based sampling at RTI International, the current implementation of grid-based sampling, and then future improvements to the methodology. So why did we start using grid-based sampling? Sample design in lower and middle income countries has long been a difficult issue. This is because it's difficult to get a complete frame. There are often outdated census data and inaccurate population estimates. We needed to find ways to implement a random probability-based sample selection while avoiding selection bias. We wanted to move away from random walks, move away from sampling with listing and relisting exercises, while representing full population across geographic locations, urban and rural areas, poverty levels, gender, and age. Specific to RTI, we developed the Geosampling methodology, which is the complex sampling design supported by Geographic Information Systems, or GIS. It's a multi-stage sampling design with stratification and clustering. In step 1, there's stratification by region. Step 2, stratification by urban and rural, using proportional allocation to select districts with probability proportional to size. At step 3, we randomly select units with probability proportional to size, followed by step 4, where again we randomly select units and cover all households within the SSU. At step 5, we select target respondents within households, for example, adults between the ages of 15 to 64. Through this, we are able to select very specific targeted areas for survey research to occur. Earlier versions of geosampling presented various issues. The methodology was originally based on 1 km² land scan population estimates, which we then had to subdivide into smaller traversable areas for our survey staff. We required the field staff to then complete censuses of all buildings found within an SSU. This led to selected grid cells yielding significantly higher or lower than expected number of dwelling units, and it also contributed to clustering. Advancements in data availability and technology have led to significant improvements on the geosampling methodology. We are now able to use better sources of gridded population estimates. These are more recent and of higher resolution, but also with the availability of high quality aerial imagery, we've been able to use machine learning to extract building outlines from aerial imagery. From this, we're then able to select random samples of building outlines within each final area cluster. In our most recent implementation of geosampling, we use an approximately 100-meter resolution population estimation raster. This was then aggregated up to larger gridded areas to create sampling units that were manageable in terms of logistics and data management. The machine learning model then identified all buildings within the aggregated area. To generate the sampling units, we started with aggregated 200-meter by 200-meter grid cells. We then assessed whether these cells could be selected by themselves or they needed to be aggregated. The goal of the project was to identify 30 buildings per sampling unit to send our survey staff to. So we needed to make sure that the population estimation within our sampling unit would be able to provide enough buildings for that purpose. In this case, 4 adjacent 200-meter cells were aggregated into one 400-meter cell to ensure we had the appropriate level of population for our survey's needs. The 100-meter cells that comprised the 400-meter cell were then identified, and imagery tiles were created for each one. From the potentially hundreds of building outlines generated for the sampling unit, 30 of the buildings were randomly selected for inclusion in the sample. There are uncertainties when identifying residential dwelling units from building footprints. The buildings may not be residential, or they may not be occupied, and the use of older imagery may not reflect current on-the-ground conditions. As you can see from this table that we created from a survey performed in India, of the 3,396 sampled buildings, 57% of those turned out to be residential. We accounted for this in our design by selecting a higher number of buildings than needed to complete our survey. We have successfully completed surveys using continually improving geosampling techniques. Much of these improvements have been achieved through the availability of improved data. This methodology is deeply dependent on population estimation rasters to point us to areas in which we can implement our model. As these data sources continue to improve, we will see further improved results. In our latest study, we used WorldPop data, which is a free downloadable source, at the 3 arc-second resolution, or approximately 100 meters at the equator. This data is top-down disaggregation of census data, and so spreads the population count for the administrative boundary across the associated geography at the grid cell level. This can lead to many cells having the same population estimate. Although this level of inaccuracy can be problematic, the data is available worldwide, by country, and also can be downloaded by gender and age bin. Other providers continue to make population estimation rasters available. One relatively recent offering is from Facebook. This data is downloadable for free at the 1 arc-second resolution, or approximately 30 meters at the equator. Like WorldPop, this is a top-down disaggregation of census data and can also show cells across relatively large areas with identical population estimates. The small cell size improves accuracy, but it does appear to classify areas within urban centers as non-residential when they appear to be populated. Currently, 140 countries are available. Landscan Global HD is a newer data set that is available to federal agencies. This data is not currently available for purchase to non-federal agencies. Landscan HD is available at the 3 arc-second resolution. This data is bottom-up, and so does not exhibit the characteristic of many surrounding cells having the same population estimate. The dataset does appear to accurately identify residential areas and has good resolution. The data is available as total population and has worldwide coverage by country. Beyond using population estimation rasters for the purpose of identifying residences for sample generation, increasingly available building footprint layers are improving our ability to create samples. This methodology has utility for surveys across the globe and not just in areas that traditionally have suffered from a lack of accurate census or address data. OpenStreetMap has building footprint data in an increasing number of areas. The greatest benefit of this data is that it is free. Although OpenStreetMap has worldwide coverage, the building footprint data is usually incomplete within countries and tends to be more available in urban areas. This data also has little attribution and so may not be accurately used currently to identify residences. Another source of building footprint data is available from Maxar Corporation. This data is available for purchase and for geographically large-scale projects would likely be cost prohibitive. The data is of good quality and has global coverage. Maxar's data is provided without attribution, but this can be added at an additional cost. At the United States level, Microsoft has generated a building footprints layer. This dataset is free to download from GitHub. The coverage is generally good, with approximately 125 million building footprints. As the layer does not include attribution, there are limits to its usefulness in generation of samples. Other commercial vendors provide building footprint data, an example of which is Building Footprint USA. This dataset is attributed with address and building type, specifically residential, business, and unknown. At the smaller scale, many municipalities and counties have building footprint data available for download, either for free or at a cost. The processing required to merge together different building footprint layers with various levels of attribution could be time prohibitive for surveys across large areas, but for smaller geographies, the availability of high-quality attributed data is extremely beneficial. So, in conclusion, we developed geosampling when gridded population datasets were of lower resolution. This led to us having to use resources to identify small areas where surveys could take place. The higher resolution gridded population estimate rasters that are now available now identify very small areas where residences exist. This has allowed us to enhance our methodology to incorporate machine learning to accurately identify buildings to form a sample. The footprints generated from this methodology allow us to randomize selection of households at a very local level. On a larger scale, companies are making building footprints available at the national and global level. This could completely transform how we generate household survey samples. However, the lower cost datasets lack attribution, and those that do provide the required information are costly. Hopefully, as these data services continue to advance, these limitations will be resolved. Thank you for your time and interest in this topic. If you have any questions, please feel free to contact me.